work at the Buenos Aires Institute of Technology, IDVA, in Buenos Aires, Argentina. We are a very small university. We are focusing on engineering. We have 2,600 students, undergraduate and postgraduate students. So we need and we want to have a huge amount of cooperations with other universities and research centers, because if not, we are too small to produce quality material. We are located in Buenos Aires with several facilities, but most of them are close to downtown, close to the Casa Rosada and the center of the city. Okay, we work with current source inverters that used to rule the world in the 70s. But after that, with the appearance of most converters, most transistors, they were left on second plane. But now, we are starting to change that based on new technologies, control techniques, and new power switches. The traditional current source inverter has a current source that could be made by a voltage source and a current regulator, or it could be just a current source like a PV system. An inductor who regulates the DC current, and 6 main switches that direct the current from the power source to the load, right? As voltage source inverters, we need a small filter, and in this case, the capacitors, while voltage source inverter needs inductors. How to get to current source inverter circuits? Well, there is a duality principle that allows us to convert voltage source inverter, especially on multi-level, to current source inverters. A voltage source inverter needs a diode in parallel with the power switch to provide bidirectional current flow. But in current source inverters, we need the diode in series with the power switch to provide bidirectional voltage control, while the current will flow only in one direction always. So in this example, 5-level diode clamping circuit, we replace the series capacitors with parallel inductors and the series switches with parallel switches. So we can get a branch of a multi-level current source. Another topology will be, that's a mistake there, this is a flying capacitors converter, 5-level flying capacitors, and we can replace the flying capacitors with flying inductors and the series switches with parallel switches. How this work? Okay, we must remember that in current source inverters, the electrons must keep going all the time. If you try to stop an electron, if you have to stop the current, an inductor will raise the voltage to the amount required to burn out the switch, okay? So in these converters, the main current must flow all the time. So what you do is to choose what path the current will follow. To have 3/4 of the main current on the load, all we need is to recirculate 1/4 of the main current, while the other 3/4 of the current will flow through the load. If we want to have half the main current on the load, well, we recirculate twice 1/4 of the main current, so only half of the main current will flow through the load. But that approach is not the best for current source inverters because there is still thinking on the voltage way. That is, we made the voltage of each phase of the load independently, okay? In the current source inverter, on the best current source inverter topologies, each module can generate the current on the load on the 3 phases at a time. And the other modules will add levels to the multi-level construction, okay? So in this case, the main current is divided by 3, with 3 inductors, as the main voltage is divided in N by the capacitors. And with one and only one of the upper switches, you decide which of the loads, of the phases of the load, will have a positive current. And we have another inductor that is sinking current from the load. So with one and only one of the down switches, you will choose which of the output phases will have a negative current, okay? Short circuits in voltage source inverter are destructive, but in current source inverter, that's the way of having 0 current in the load. If I turn on this upper switch and this lower switch, there will be a current path for the current of this inductor to flow to this other inductor, and there will be 0 current at the exit. This leads to really modular converters where I can add as many modules as I want to get more and more levels at the output and to get fault-tolerant capabilities. Oh, this is supposed to be a very nice animation, but something failed. Okay, so let's keep going. Okay, so I could have a 4th model on a hot swap configuration, and if I need to, if something happens with any of these models, all I have to do is short circuit this inductor into the main inductor to allow the energy of this inductor to discharge on the main inductor, and then just start switching the transistors of the 4th module, and because all the inductors have the same value, the current on the hot spare module will rise at the same ratio that the current of the failed module will fall down. So the main current will not see any different on the current that is going to the load, and the load will suffer a small distortion because I cannot switch all the current that I want all the time, but that distortion will be very small as the discharge of one inductor or charge of the other last, okay? And this kind of perturbation is easy to handle with any power system and it's not a problem. So reliability of these converters can be increased as much as you want. Okay. Now with wide bandgap semiconductors, we can have a very increase in efficiency, reducing the size, and we can also increase in a great amount the switching frequency. So we have smaller devices and smaller passive components, especially inductors. What will happen when we have high-temp semiconductors? Well, you will have infinite power in a 0 volume, in theory. So this will be, if we could have high-temperature superconductors, well, you can have kilowatts in centimeters, squares, or cubic centimeters. Okay, so this will be the converters of the future. which is not easily going to happen with capacitors. Okay, so we use this multi-level topology, and what we want is to use a very precise control to get many features at the same time. The first choice is to use sinusoidal PWM, but it's not easy to get flexible control of the converter. So we're going to use a special control based on this model. Okay, this is one. This is the switching combination for one model. We have 9 possibilities with 3 0 states, which adds one more level than the voltage inverters, and this is the representation equation of the converter, where we add to the standard converter the power source from a voltage source and the 2 inductors that I showed you before. Now, we had to represent the load, where here are the currents of the inverter, and this is the load with the capacitor filters, and this leads to a whole system that could be represented in these equations. Okay, now, what we're going to do is a controller on a digital platform. We use FPGAs. So first thing we're going to do is an Euler transformation, which works quite good for us because we are working on a 50 megahertz FPGA with only 9 seconds to do all the math. So this works pretty good. Okay. Now the discrete version changed the equations into something that has almost the same form, but considering the sample time. And we do a finite control set multilevel predictive control that with 3 main control objectives. First, track the voltage at the load. Second, perform a balance of the internal currents. As in any multi-level, you need to balance the internal capacitors or the internal inductors, and to minimize the switching frequency, because we are trying to use, even if we try to use the maximum frequency for the math, we want to reduce the switching frequency to increase, to reduce the switching losses. Okay. So we, as in any standard predictive control, we are going to use a cost function with different weighting for each factor. Now, this is a second-order circuit, so we need 2 time steps for a change in the input to occur on the output load. So we're going to predict we are going to use a model that tries to predict the output in k+2, while the input changes are carried out at instant k. Okay. With this, we have only 1,458 switching states, with each 9 per model, 3 models, and 2 because we had 2 states on the voltage input switch. It's a few, okay? To avoid a variable delay, we change the switches only at a fixed instant of time, that is k+1. Well, cost function, with the first term is the voltage at the load, the second one is the balance of the internal currents, and the third one is to reduce the commutation not only on the current source inverter per se, but also in the power source, which the cost functions use the difference on the square of the voltage for the output voltage. So the reference used with this occasion, it's very nice coefficients. And there's something wrong there too. And this is the cost term with the internal currents, and this is the cost term for the number of switching. With that, we can have this voltage at the load, and this is the voltage on one phase, this is the current on one phase, and this is the actual output of the multi-level current source inverter. And with that, we have a ripple current in the main inductor that is only 1 or 2%, which is pretty good. Distortion, of course, the distortion, the THD at the output of the inverter is huge, but with the small capacitor bank as a feature, we reduce that to only 1.2% in the output current, which is pretty good even for the IEEE standards. So this control can achieve a very low THD. And what happens if we bother the control? What happens if we change a couple of things? Well, we have a step change on the output voltage reference, and we see a small disturbance in the output voltage, but the current change is very smooth. As you see here, we have 3 levels up, 3 levels down, which is the 7 levels plus the 0. And now we lost a level because the current is smaller, but we don't lose pulses here. We have the same amount of switching states in the middle, so there will be no extra distortion, no extra THD. And now because we have too much current on the input for the output current that we want, we change the input current, and as the input current goes down, the output current remains constant, and now the converter can use all the levels again because of the reduced input current. This is a comparison between sinusoidal PWM and the controller we are proposing, and these are the internal currents and the inductors. Because of the special switching combination and the relationship between the phase of the reference for the sinusoidal PWM and the output current, these flat levels occur in the switching. When the output current is at the top, the only way to get that is to turn on the 3 switches at the top for a while. So that's why we have these flat zones here. And the sinusoidal PWM, even if it grants an internal current balance, the balance has a very big error, which is not acceptable. And with this control, we can reduce the unbalance of the internal current, and we can be sure they will keep balance even if we have distortions, harmonics on the load, and switching unbalances. Okay, this is the test bench. This rack here is full of inductors. It weighs like 80 kilos or something. Yeah, inductors are heavier and bulkier than capacitors, but an inductor is a piece of copper around a piece of iron. So if you don't let it overheat, it will last forever, which not happens to capacitors. A capacitor will turn into fire, will explode. It's just a matter of time. It's like a time bomb, okay? And we designed this converter as a small model of a huge converter. So no SMD transistors, no fancy connectors. It's rough and to allow this to escalate to higher powers and not to mask problems that we will have on a real converter because of use of high technology. We use the FPGA, the acquisition system that we developed to get to the 50 megahertz we want to as processing speed. And well, the rest of a microgrid we are working on the rest of the equipment. Okay, so with this control, we can get a lower switching frequency, which is an improvement from sinusoidal PWM, which means on the higher efficiency. We can guarantee the balance of the internal currents, and we can do all that by also meeting the regulation on THD. Issue on this is that the control strategy depends on the system parameters, so we had to do some observer or something like that if the parameters of the system have to change. And what are the drawbacks? Well, huge amount of computational power is needed, so we use an FPGA to parallel compute all the things we have to do. The FPGA also do the synchronization with the grid and other communications like communication with the sensors and communications to the monitoring system. And of course, a variable switching frequency, which is a problem inherent of this kind of control. Okay, thank you.